Hello everyone, I'm Christos and together with Kemal and Abdul, we created a comprehensive security analysis of the open source Python ecosystem. So, Python is the most popular programming language today, powering everything from web development to machine learning, data science, and automation and developer operation. But how secure is the Python ecosystem? That's what we wanted to find out. Our central research question was, is the Python ecosystem threatened more by vulnerabilities in its own project code or by, by vulnerabilities inherited through dependencies? So, to answer this question, we used a two-component approach. First, we analyzed approximately 3,000 confirmed CVEs from the Morphix's dataset to understand direct vulnerabilities in Python projects. Secondly, we used OSV Scanner, which is implemented from Google, to identify vulnerabilities in the dependencies of these projects. Let me show you how component 1 worked. Here you can see our SQL query that filters for Python projects by checking repository URLs and file extensions. This query connects to the Morphix's PostgreSQL database. When we run this, we extracted 2,929 confirmed CVEs affecting 780 unique Python repositories. You can see the data. It's loading here. This data set includes CV IDs, severity scores, CWE categories, and affected repositories. Now let me show you our analysis. First, we analyzed when these vulnerabilities were disclosed by year. This graph shows CV counts by year. Notice a significant increase after 2018, peaking at 590 CVs in 2023. This suggests increased security scrutiny and more systematic reporting in recent years. Next, we looked at severity. We classified CVEs using CVSS scores into low, medium, high, and critical. The results showed that nearly half of all Python CVEs are high or critical severity. This is concerning and highlights the serious security challenges in Python projects. We also analyzed weakness types using CWE categories. The top vulnerability types are cross-site scripting with 358 cases, path traversal with 139 cases, and improper input validation with 133 cases. This pattern mirrors typical web application vulnerabilities. The top vulnerability types are cross-site scripting with 358 cases, path traversal, and improper input validation. Finally, we identified the most vulnerable repositories. Django leads with 121 CVEs, followed by CPython with 120, and Apache Airflow with 109. These are foundational frameworks used throughout the industry. The final step of component 1 was identifying which of these repositories are published on Python's package index. We found that 313 repositories, which is about 40%, are distributed as PyP packages. This is important because it means these vulnerabilities directly affect end users who install these packages. Now I will hand it over to Kemal, who will demonstrate component 2, where we scanned these PyP packages for dependency vulnerabilities.
Thanks, Christos. I'm Kemal and I'll show you how we analyze dependency vulnerabilities using Google's OSV scanner. Building on Christos' work, we took the 789 Python repositories and verified them against the PyPy-JSON API. This ensured we were scanning the correct and actively maintained packages. Here you can see how we queried PyPy's API for each repository. The API returns package metadata, including versions, dependencies, and maintainer information. And we use this source link to see if matches with the data in the Morphix's database. After matching, we had 313 confirmed packages ready for scanning. Now let me demonstrate the actual scanning process. First, we cloned each repository locally using this command. This is necessary because the OSV scanner needs to analyze the dependency files directly. And here is an example of OSV scanner running on the Flask app builder repository. And the command we use is quite straightforward. It's just OSV scanner format JSON recursive and the path of the directory of the repository. When I run this, it will produce a JSON output containing all the detected vulnerabilities, and each entry includes the CVE ID, an affected package, severity score, and version information. And we run this process on all of the repositories that are ready for scanning. And we collected all the individual JSON files. Here you can see all the JSON files we had in this process. And it was successful around 70% of them. And next step was parsing and analyzing these results. We wrote a Python code to flatten the nested JSON structure and extract all vulnerability records into a unified dataset. The results we found were striking. We found 3,367 dependency vulnerabilities representing 709 unique series, which are affecting 117 repositories. That is significantly more than the direct vulnerabilities. When we look at the timeline, we see a different pattern than direct CVEs. Dependency vulnerabilities are overwhelmingly concentrated in the recent years. 63% were disclosed between 2022 and 2025. And the severity distribution was also concerning. 49.2% of dependency vulnerabilities are high or critical severity, which is slightly higher than the direct CVEs. And the weakness types are different too. While direct CVs focused on web vulnerabilities like XSS, dependency vulnerabilities show more computational complexity issues. Regex complexity with 48 cases and resource consumption with 44 cases. This reflects the nature of modern Python libraries, which are handling data processing and machine learning. Finally, here are the repositories with the most dependency vulnerabilities. Russell leads with 2010. This is followed by Flask App Builder with 132. And these frameworks have extensive dependency trees, which is the probably the main cause of their exposure. Now I'll pass it to Abdul, who will synthesize our findings and show you what this all means for Python ecosystem security.
Thank you, Kemal. I am Abdul, and I will bring everything together to answer our research question. Let's recap our complete process. We extracted Python CVEs from more fixes and then matched them to PyPI and then scanned with OSV scanner and analyzed the results. So let's go to what our results were. For our comparison table, here's our key finding. We discovered 2,929 direct CVs in Python code and 3,367 in dependency vulnerabilities. That's around 15% difference. Dependencies actually contribute more vulnerabilities than the code developer write themselves. For our severity, when we compare severity, both are concerning, but dependencies edge out slightly. 49.2% for dependencies and 48.5% for direct code. Let's go to our timeline comparison. So the temporal trend tells an interesting story. Direct CVs peaked in 2023 and then stabilized. But dependency vulnerabilities keep climbing. 63% emerged just in last 3 years. This is the growing attack surface we need to worry about. Let's go to our CWE comparison. The vulnerability pattern differs significantly. Direct codes show traditional web vulnerabilities like XSS, path traversal, input validation, and dependency shows computational issues, regex complexity, resource consumption. This makes sense. Modern Python libraries handle complex data processing, ML workloads, and API operations. When we look at impact distribution, certain repositories are hotspot, like Django and CPython have high direct CVs count because they are widely scrutinized, but Rasa and Flask app builder show massive dependency vulnerabilities count. Like for Rasa it was 210 and for Flask app builder it is 133 because they pull in dozens of other libraries. Let's go to our research question. Is Python threatened more by its own code or by dependencies? I will say both, but dependencies are the growing concern. While direct code vulnerabilities are being addressed through better practices and security scrutiny, the dependency supply chain continues to expand and introduce new risks at an accelerating pace. So for our conclusion, what are the key takeaways? What should we take away from this study? First, don't just secure your code, but to audit your dependencies as well. They contribute 15% more vulnerabilities and the threat and the trend is accelerating. Secondly, use software composition analysis tool like OSV scanner in your CI/CD pipelines. Automated dependency scanning should be standard practice. And third, pay attention to computational complexity vulnerabilities. Regex attack, resource exhaustion, especially if you are using data processing or ML libraries. Thank you for watching.